Hey everybody, Daniel here from Basement Tech. Well, regular watchers of the channel will remember that I'm converting the CNC Shark behind me from its proprietary controller to one driven from LinuxCNC. This is the next video in that series, and honestly I've been dreading it just a little bit. I'm going to talk about the configuration of LinuxCNC. I have to do a lot of this on the screen, which is why I'm kind of dreading it. But I hope you'll stick with me, and it will become clear by the end of the video just how the hardware is reflected in the configuration that's done in LinuxCNC. I'm also going to touch in the middle of the video on just what it costs to do this conversion, and I hope you'll stay tuned for that bit as well. That's about at the 8-minute mark if you would just want to jump there. Well, I thought a good place to start would be here with more of a block diagram. Sometimes I realize when I'm explaining things and pointing at wires running all over the place in the back room on the physical system itself, it's hard to get an idea from a little bit of a big picture of what's going on. You can see pictures like this drawn all over the internet, and many of them are in different levels of detail and designed to show different things. I don't mean this one to be a schematic diagram so much as an indicator of the overall layout and signal routing that's going on in the system. So let me just start at the high level. And before I do that, I do want to say, I think this discussion of the overall design and layout of the system will help when it comes to the description of how do we configure LinuxCNC, and why is it frankly so easy to do when you have this particular hardware configuration. Second point to be made before I dive in is that, as I said several times in several of the videos, I had these components on hand, so these are the ones I used, but I have to admit, in the end, it did turn out to be a pretty convenient set of hardware to use. So let me get rid of my mug here so you can see the entire diagram, and I'm going to start here on the left. Simply some PC. I happen to have this i7 one, and it has plenty of horsepower to do the job of running LinuxCNC with Linux's real-time extensions to the kernel. The software gets loaded onto the hard drive of this device, and that's kind of the heart of the system. Plugged into that is this Mesa 5i25, and if I had to pick one component in the system that's kind of the magic, this is the one. It plugs into a PCI slot in a standard PC, and it provides a lot of functionality. It provides signal routing very simply from the software out through this DB25 and onto the rest of the system. It actually, in this system, does the real-time step generation. LinuxCNC does the path planning, but then it sends down those signals, those step planning steps about once in 1 millisecond to this card, which then goes on to generate all the individual pulses which move the motors. Finally, it comes with firmware. Firmware can be used to do signal routing between signals that are called out in the software and the signals that end up on, and which specific pin those signals end up on. You're going to see this is a lot of the configuration that we did in LinuxCNC, and the fact that this card knew that I was going to connect to a G540 made that a little bit quicker and easier. I'm going to quickly just mention this Mesa board has two parallel outputs. So it has, it would normally have sort of two breakout boards. One of those breakout boards is built into the Gecko G540. The second is going to be a discrete one that I purchased from CNC for PC that I'm going to use just to get some more signals to control some more fun things. As I talk through the right side here, you'll see that we're somewhat limited on inputs and outputs. But there's plenty for any basic system. So this second breakout board is definitely optional, but it does highlight that this Mesa card is very powerful in that it could potentially run two Gecko G540s. I'm not going to do that, but I will use this for signals for driving things like spindle control and laser control, for example. So the main one comes out the back on a DB25, which is standard for all of these systems sort of since time began. And that's in the physical system back there. It's a white cable with a DB25 on each end. That routes from the back of the computer via this Mesa 5i25 into the Gecko G540, which you can think of as having two primary functions. One is a breakout board, and the other is amplification, to take the small signals coming out of the computer and amplify them to the point where they'll actually move motors. That's a very standard function of every stepper controller and nothing unique in this system here. What is unique is that the signals as they appear on this this DB25 are internally routed to the amplifiers within for the motors, and internally routed to this this terminal strip that's on the back of the Gecko G540. And it's done in a very deliberate way, knowing that this is the way a typical layout will happen. In other systems where the amplifiers are separate discrete boxes, like the CNC router that we have at the shop, I have to do this wiring separately and do that myself through use of a breakout board like the CNC for PC C11 breakout board. I don't have to do that here. It makes my life very easy. So you can kind of see the theme. The Mesa 5i25 knows about a G540. The G540 has very convenient routing via standard connectors to motors and limit switches. So that makes this design very simple. I realize as I move from the top of the diagram, which is pretty straightforward, to the bottom one, it looks like there are an awful lot more lines. But let me assure you, the simplicity continues throughout the rest of the diagram. Let me eliminate the red wires and talk about just the black wires for a minute. These inputs into the Gecko G540, which end up all the way back at LinuxCNC, are pulled low by the switches. And I've used that language a few other times in a few of the other videos. And what pulled low means, when these switches close, they connect that pin to ground. The ground is held high internally by the G540, and high means 1 or yes or true. And when the switch is activated, it pulls that pin down to ground, which goes all the way back to the power supply. And that indicates to the software that something has happened. It goes down to false or 0 or off. And the software can detect that as a limit switch. So that's kind of point number one. And you notice all of the black wires end up back at the same place. We have two power supplies being used in this system. One is the 48-volt power supply for the Gecko G540 and motors. And for signal level things, we have a 12-volt power supply, physically two separate things like I've shown here. But do note that the ground wire, the black wire from those power supplies, also connect together all to this common point here. So that's signal level 0, and that persists throughout the whole thing. Let me turn the red wires back on, and you can see that the red wire from the 48-volt goes exclusively to the G540 to run the motors, and the red from the 12 volts goes out here to these inductive limit switches, which require more than just a simple switch. It requires 12 volts in order to switch this blue wire up and down. So I think it's pretty straightforward. You can just think of these signals on this strip here, the terminal strip on the back of the G540, being pulled down to power supply ground by the switches to which they're routed. So that, I think, is fairly straightforward. I did not show the e-stop switch, but it's very similarly wired. There's a black wire that comes off of one of these pins. When the e-stop closes, it actually opens that switch. It's a normally closed connection that's open when the e-stop button is pushed, so it releases the corresponding pin from ground, and the software can detect that. So that's the overview. Let's jump into the software, and I can show you how this wiring diagram and physical configuration is reflected in the software. As I'm fond of saying, before I do that, let me just touch briefly on cost. This is the cost of switching out your proprietary Shark controller for something more generic. It's not trivial, and that's the main reason I wanted to highlight it here. A lot of these things I had, so I didn't bear all of this cost, but if you were just to go buy these things, this is about what it'll cost. A Gecko G540 on the web today is $289. You can pick up PCs very cost effectively. This Mesa card is about $90, and so on and so forth. And when you add it all together, you do end up in sort of the $800 range, and because you may not have the same junk box that I have, you might end up closer to $1,000 to make this conversion. Not trivial at all, but just something to consider as you think through this. Well, the first thing we need to do when thinking about configuring LinuxCNC is derive some of the little numbers that go into the little boxes. The first one relates to just basic motion. I did type up these notes, and I'm going to try to attach them to the description. Hopefully it won't be too long. But relating to just simply basic motion, the first part in the motion equation is how many steps per revolution does the stepper motor require. Now, that's a little bit complicated here because NextWave is very, very close-lipped about their motor specifications. Either intentionally or unintentionally, they took all the labels off. However, I did find published on a couple of web posts a couple of numbers that allowed me to pattern match it together with a motor that I am familiar with, which was this one. That motor, like many motors, has 200 steps per revolution. Very common number. So I was pretty confident moving forward with that. So that converts steps from the LinuxCNC, which go through the G540, into rotational motion from the motor. Now, how do we turn that rotational motion into linear motion? Well, that's the lead screw. Before we get there, we have to note that the Gecko G540 has 10 times microstepping, which turns our 200 steps per revolution into 2,000 steps per revolution. And you can see we're building up some pretty good resolution here. Now, the lead screw, the way I got to that number was frankly just a little manual experiment. I manually spun the lead screw around 2 revolutions and saw that that moved us about an inch. Since that was a nice round number, I felt confident moving forward with that. I did go back and fine-tune that number. So 200 steps per revolution times 10x microstepping times 2 revolutions per inch leads us to 4,000 steps per inch, or less than 1,000th per step, which is pretty good resolution. So that gets us to basic motion. Remember that number, and you'll see where we fill that into the LinuxCNC configuration utility. The next big piece of work, and maybe the biggest, is where do we connect all these limit switches now that we have the capability to have them? I flashed by some pieces of paper very quickly when we were in some of the other videos, so let me just slow down for a second and show you what those are. In the notes, I tell you where to go find this document, which says, hey, what do those 25 pins that are coming out on that DB25 look like in terms of signals? Here that is. Now, it doesn't make a lot of sense until you combine it with the Gecko G540 specification of its 25-pin input, which in fact is the same as the 5i25 output, and you start to see some things that make sense. I noted when I was talking about the block diagram that some of the connections are made internally, and that's really good for us. And you'll see they're also made by default in the configuration utility for LinuxCNC. All of the motion and other signals which are, I would call required, the e-stop and the charge pump, for example, those connections are made internally, and that's where that Gecko G540 is acting like a breakout board. The place where we want to connect some of the external signals, in our case the limit switches, are provided on these pins on the DB25, 10, 11, 12, 13. They end up on the terminal strip on the back at 1, 2, 3, 4. And if I jump over here to this 5i25, they appear here on 13, 14, 15, 16. Now, for your convenience, I kind of combined all that stuff into this little table here, which says the X limit. You know, we have two switches in series there, and they get tied to pin 1 of the Gecko G540's terminal strip, which is IO13 in terms of the 5i25, and is called 013 in the pncconf utility, which is what I keep referring to as the Linux CNC configuration utility, and so on and so forth. So if you connect your limit switch to pin 1 on the Gecko G540, you'll call that 13 inside of this pncconf utility. All right, well, having looked at the system block diagram and derived some important numerical values, it's time to actually do some configuration. What you see in front of you is the result of me loading a CNC Linux ISO. What that means is it's an image, a disk image, that contains the operating system configured in such a way as to be friendly to Linux CNC. I didn't really want to learn how to do all that, so I took that option. You'll see in the top of the notes the link to the place where I downloaded that ISO. In terms of configuration, it's been made a lot easier from what you might call the dark days of Linux CNC, where text files had to be edited. Some very benevolent software person developed this Linux CNC configuration wizard. So we're going to use that, and it's really the first step before you even perhaps plug in the motors. The first step that you'll want to take in configuring Linux CNC. A couple of notes right up front. Number one, do remember this is for my hardware configuration. It's for the specific pieces that I've chosen. However, I think you'll see that it's pretty straightforward to extrapolate from what I'm going to show you to what you would have to do for some other hardware configuration. For example, if you had a different Mesa card, you'll see that the configuration wizard self-configures itself for the various cards that you choose. The second thing is, you know, from a safety point of view, please do your own research. Make sure that you feel comfortable doing the kinds of things that we're doing here and in any of the videos in this series before you proceed. You obviously can hurt yourself by moving the axis in an unexpected way. So do some research and use some caution when you're doing this kind of configuration. Okay, well, I'm going to start up the Linux CNC configuration wizard. Honestly, I'm not sure where this name came from, but it's an extremely useful piece of software, and I'm really glad that somebody invented it. By the way, you might also wonder why I'm not using some kind of a screen capture. Well, as I said, I loaded an ISO with a pre-configured operating system, and I don't really want to corrupt that with any other applications that may affect the way Linux CNC runs. So hence you have to endure my iPhone aimed at this monitor. So let's get started. I think you're going to see that this this utility is very straightforward. Let's start by pressing the start button. Right up front it says, do I want to create a new configuration or modify an existing one? I'm going to create one so you can see what it looks like in its virgin state. Normally, if I'm coming in to make a change, I'll just modify the configuration that I already have. Leave this check mark checked so that it will create a desktop launcher using the new configuration that you've created. So moving forward, it's just asking you basically what are some of the basic characteristics of the system you're using. Well, it's an XYZ system. I can give it a name. I think I called mine CNC Junior because CNC Senior is down at the shop. And I left most of the rest of it the same. I did change this one value here. There's a lot of talk about latency in a lot of the configuration documentation. Because we're using the Mesa card, we don't have to worry about that too much. The software itself is not creating the steps for the motors, it's the Mesa card. However, I did find that reducing this number from a millisecond down to 250 microseconds did seem to help the performance of the system. So I'm going to make that change. I've got one Mesa card, and I left the rest of these things the same. Moving forward now, it wants to know, again, a little bit of basic information about how you want LinuxCNC to be presented to you. You saw in a couple of the videos I was able to change the graphical user interface, and that's because the way the system is architected, it's a layer on top of, call it the motion engine. This GMO CAPI one is a lot more attractive and I think functional, so I'm going to choose that. The selections down here I did leave the same. You might want to look into what those mean and adjust them for your own preferences. This page talks about additional tabs that you can be presented with in that GMO CAPI graphical user interface. I'm going to leave those off for now for simplicity's sake. Now we're getting into the real meat of the utility. I did say that I had a 5i25 card, so that selection comes up by default. However, my firmware is designated exactly like this with a little sticker on the card. And basically what it means is expect to have two Gecko G540s connected. I only have one, and you'll see the changes I make to indicate that to the system. I'm not going to get too deeply into configuring the spindle at this point, so I'm going to leave these numbers the same. However, I am going to change a couple of these at the bottom. I'm not using any encoders. I don't have any servo motors, so I can reduce that to 0. Initially, I'm just going to have one spindle control, so PWM references spindle control. However, at some point in the future, I am going to use PWM to control a laser, so I'm going to leave that at 2. You might want to change that one to 1. And then in terms of step generators, as I mentioned, I have one Gecko G540, and so that means 4 axes, so I'm going to change the number of step generators to 4. The system will bark at you if you don't press this accept component changes, because what it does, based on that press of a button, is that it auto-configures these tabs for the choices you've made. I mentioned back in the block diagram that the 5i25 has 2 parallel outputs. One comes off of the card on a dual pin header, and the other comes out of the back panel on a DB25, which connects to my Gecko G540. That's the one I'm going to configure. The system is smart in that it knows for each axis, for each motor, I need to generate steps and indicate direction. And you see those indicated here pre-configured as step and direction times 4. They're labeled 0, 1, 2, 3. In computer parlance, a lot of times you start counting with 0, and that's why that's the way it is. So let's look at 0. That's going to be my x-axis, so I'm going to change that to axis, main axis, x. And as you can guess, I'm going to change 1 to axis, main axis, y. And finally, 2 is going to be axis, main axis, z. I do intend to use the 4th axis for a rotational axis, so I'm going to go ahead and configure that at this point as axis, main axis, a. You can see when I changed the step generation, it also changed the direction correspondingly. We might as well configure the e-stop. That's pretty straightforward. It's one of those inputs that I called hardwired, in that it's internally wired inside the Gecko G540 to come out of, I believe it's pin 10. Let me double check real quick here. Yes, so the e-stop is on pin 10 of the DB25, and if you remember the little table I showed you in the beginning part of the video, that's on number 3. So it's already configured as an input, so I'm going I'm going to select, I believe it's operation, no, we'll find it, e-stop in, so let's choose that one. Now our e-stop is configured, so when I wire my e-stop switch to pin number 10 on the terminal strip on the back of the Gecko G540, that input will be recognized. Now the charge pump requires just one more step, and it's hardwired again under this 005 input. However, it's considered an output, so I have to choose output first on the pin type side, and that gives me a different set of selections over here under function. So I believe that's under control, charge pump. Okay, so we have the X, Y, Z, and a future A axis configured. We have the e-stop input configured, and we have the charge pump configured. So on my Gecko G540, I switched the charge pump switch from off to on, and everything should be good. Now let's get to the part where many of the questions come up. How do I configure these darn limit switches for LinuxCNC? Believe me when I tell you, it's as straightforward as what we just did. Referring again back to the little table that I showed you way in the beginning, pins 1, 2, 3, and 4 on the Gecko G540's little terminal strip on the back are represented as 13, 14, 15, and 16 here. So my two switches, my X-axis switches that are wired in series are connected to pin 1 on that terminal strip. You know, as you've now recognized, this configuration utility is a bit smart. It presents you with, I think, choices that are relevant. So typically those 4 inputs are used for limit switches. So let's go ahead and see what choices we're presented with. Wow, those look relevant to me. In my case, the X-axis switches are in series, and the X- switch is also used for homing. So I'm choosing limits, home, shared input. Come down to main axis, and I said that I'm using one input for both the X minimum and X maximum, and it's used for home. So I'm going to choose that selection. Let's move on to Y. Now Y is different. I have 2 separate switches wired to 2 separate inputs, pin 2 and 3 on the Gecko G540 terminal strip. That's input 14 and 15. So 14 is also going to be shared. This is the Y minus, the Y minimum, and it's also the home switch. So I see here Y minimum limit plus home. Again, a very logical and appropriate choice it's giving me. Let's move on. The other switch is used only for Y-axis maximum. It's not shared as a home, and it's a switch unto itself, unlike the X-axis. So let's just call that Y maximum. Now you're going to see something crazy happen when I choose this. For some reason, it resets this Y minimum home selection. I don't know why that happens, but if you go back and just re-choose it, limits, choose Y minimum plus home, now they both stay as you would expect. Again, I don't know why that happens, but we do end up with the right selections in the end. For the Z-axis, you say, wait, there are no more inputs. But as we did on this side, we can change these 4 pins from inputs to outputs. I'm going to use pin 4 on the G540's terminal strip, represented and decoded by the little table I showed you in the beginning as 016. So I've changed it to input. Now I'm going to get selections that make sense for an input. It's going to be shared. It's at the top of the travel, so that makes it the Z maximum plus home selection. Voila, there we have it. All of our hardware connections are configured, many pre-configured for us by the fact that the the 5i25 knows it's connected to a G540, but I think relatively straightforward in the end. Okay, I'm going to do a little bit of cheating in this next section of the video. I have in the background an instance of the configuration utility looking at my my configuration file that I've created for this particular machine that I'm working on, and what I have in the foreground is the one we've been editing from the default state of the configuration. And I'm doing that just because I don't remember all of the numbers, that some through trial and error, and a couple on this screen that are in that category. Now you can see we're talking about individual axes. We first talked about the configuration of the machine. We talked about how the hardware is connected. Now we're looking at each individual axis. So remember that number, 4,000? This is the place where it goes. 4,000 pulses per inch. In terms of maximum velocity, I actually found this almost unbelievable, but the axes are apparently capable of 200 inches per minute. It's pretty quick, but it does seem to be, a good number for this particular set of hardware that I'm working on. Maximum velocity is a number that's kind of derived based on feel. The number that I arrived at for X that seemed to accelerate and decelerate at the correct rate is 10. Others may have other numbers, and there may be a theoretically correct number, but I'm not really aware of that. So those are the only two numbers I'm going to change, or sorry, the only three numbers I'm going to change on this screen. These numbers up here refer to the actual waveforms that are played out by the G540 and are filled in by default numbers. And these are not numbers I'm going to change, need to change for the x-axis. So moving forward and summarizing again, I changed these few numbers down here based on the numbers we derived earlier. So the second page of the configuration of the x-axis has to do with homing. I'm actually going to, again, cheat a little bit and flip to the numbers as I configured them based on a few things. These have to do with the exact placement of the limit switches, which direction is negative for homing activity, and what speeds should be used for those kinds of activities. So you can see the numbers I've chosen, and it's really as simple as just editing those into your screen for your particular set of hardware once you've determined what these things are. There are some great write-ups in the LinuxCNC manual for these kind of things, and you can access that CNC documentation. You can get to the LinuxCNC documentation through this little menu tree, and I would recommend doing that when it comes to this page. These numbers, again, are very specific to the hardware I have, and they made sense to me, some based on feel and others based on measurements, but in the end I think they worked out well. I'm going to kind of skip over Y because it's very similar. Change these few numbers down here. The X and Y are have the same scaling factor, and you set appropriate maximum velocities for Y. I think in the end I didn't like Y going at 200, so I did change that if I'm not mistaken. So let's take a look at Y. No, I guess I did leave it at 200, and an acceleration of 10 seemed to make sense. Moving on to Z, it's very similar. Z actually has a resolution that's twice that of the other axes. So in stepper scale, that needs to be 8,000. And again, based on experiments and measurements, I found that a maximum velocity of 50 made it run in a way that made me comfortable. So those are those choices. And again, based on how you set up your z-axis, you would set up this homing page in such a way as to have that make sense. Do notice that there are some negative signs on some of these numbers, and again, the documentation covers this very clearly, and I would recommend reading and understanding that and then making these changes in a way that makes sense for your hardware. So when you get all the way till the end, and I'm going to quit out of changing my configuration file because I don't want to change it, you just get to this point, and when you get all the way to the end, you click Done, and it will create, as I said, this launcher using the configuration that you've just created. So the configuration has been built and saved. Do you want to quit? I'm going to say yes. So I actually have two configurations now. I'm going to delete this one because I don't ever want to use it. I want to use the one that I know works, which is this one. So if I double click on that, it'll bring up LinuxCNC, and I'll use my new configuration. Now, I've done that in a lot of other videos, and I kind of wanted to focus on configuration here, so I'm actually going to end the video here. Again, it's worth repeating that your particular hardware may require adjustments to this basic process, but the basic process itself doesn't change. I would invite you to put your learnings and ask any questions you might have in the comments below so that we can all learn together. This is the first time I've done this, so I certainly may have set something up in a way that maybe doesn't make sense or isn't theoretically correct for LinuxCNC, so please let me know that. However, the system seems to run very well using the configuration that I have set up. And as represented in the system diagram at the beginning of the video. I know this video got long, but I couldn't think of any better way to talk through this, so I hope you appreciate this video, and we'll stay tuned for other videos which will include things like how to configure a laser in a system using LinuxCNC. So thanks, talk to you soon, bye.